Hello, and thank you for coming to watch my talk. My name is Jeger Broxterman, and I'm a second year PhD student working at Leiden University. And in my PhD, I focus on analyzing suites of hydrodynamical cosmological simulations and weak gravitational lensing in these simulations. And today, I'll be talking to you about the impact of baryonic physics and cosmology on weak gravitational lensing convergence peaks in FLAMINGO. So, weak lensing peaks are the local maxima and weak lensing convergence maps, as you can see in this figure on the right-hand side. The yellow circles indicate these weak lensing peaks, and they are simply pixels with a higher value than their neighbors. It has been shown that these peaks are complementary in constrained cosmology, compared to only using two-point statistics, such as the correlation function, as these peaks probe additional information that's not captured by only using the Gaussian information probed by these two-point statistics. However, before we can use these peaks for our next generation surveys, such as Euclid, we need to really understand baryonic feedback, which also reshapes the matter distribution on nonlinear and mildly nonlinear scales. And in my PhD, I've been working on analyzing these statistics with the different baryonic feedback variations to quantify these differences. So for this, I've been using the FLAMINGO Cosmological Hydrodynamical Simulation Suite. And I'll not go into detail because Mathieu Schaller is also giving a talk. But for my project, I'll say that there's a lot of different variations, both baryonic physics implementations as well as cosmology variations in 1 gigaparsec boxes, and that the initial phases of these simulations are the same, and as much as was possible is kept the same, and therefore we can really use this as a playground to quantify these baryonic differences that I'm interested in. And these simulations are calibrated to two observables, namely the galaxy stellar mass function at redshift 0, which is shown in the left panel, as well as the gas fraction of low redshift clusters, which is shown in the right panel. And for my analysis, so for these weak lensing peaks, this ensures that at least the ratio of both gas and stars to dark matter is realistic in the objects that I'm probing with these peaks. So I'm using the Flamingo light cones. These light cones are a set of shells which are centered around the virtual observer in the simulations. And for each of the particles, the time when it crosses the backward light cone of an observer is recorded. And they are projected onto these shells, and I can use them for my weak lensing estimates. So I'm using mimicking a Euclid-like signal. So I'm doing a ray-traced weak lensing analysis, assuming a simple Euclid-like source redshift distribution, and also applying some noise, and also smoothing the maps. And then on the final maps, I determine my peaks, and then I study the characteristics of these peak distributions. So, for example, the fiducial baryonic impact of Flamingo is shown in this figure. So this figure shows two curves. The purple curve shows the L2.8 M9, which is the fiducial baryonic Flamingo signal, and the black curve is the corresponding signal as measured in a dark matter only run, so without any baryonic physics. And the bottom panel shows the ratio of the hydrodynamical to the dark matter only signal. And here we identify different regimes, namely the low kappa regime below approximately 0.1, which we find is dominated a lot by the noise and the smoothing and the choices that are applied in the pipeline. And therefore, when actually comparing to observations, this is going to be difficult, as you need to really carefully model all these survey characteristics. And additionally, for the high kappa, we see that they are dominated by by the combination of Poisson noise as well as cosmic variance, as indicated by the gray shaded region. So this indicates truly a fundamental limit to using these peaks. But in the intermediate regime, we see that there is a clear baryonic impact, and that we can also clearly understand. And therefore, these peaks could be highly useful in constrained cosmology. So the fiducial impact is roughly 10% at kappa of 0.1, and you see it decreases for larger convergence. And we can understand this by first considering different feedback. So that's what's shown in this plot. So now I consider 5 different flamingo variations, which have all been calibrated to a different gas fraction in low redshift clusters. as indicated by the F-gas plus, for instance, 2 sigma. And the simulations with increasingly stronger feedback are indicated by the increasingly darker blue curves, as there's been more gas removed from these clusters, so there's stronger feedback. And you see that they also have an increased suppressed weak lensing peak number density. And we can understand this behavior by considering the impact of baryonic feedback on single halos. So when there's more feedback, there's stronger feedback, there's more gas removed from the centers of these halos. They are less overdense, and therefore we also expect the weak lensing signal, which is proportional to this overdensity, to also be less. So we expect less high kappa peaks for these simulations with stronger feedback, and that's also what's shown here. Yeah, and additionally, when this happens early on in a halo's life and gas is removed, there will consequently also be less gravitational attraction, and also less dark matter will be attracted, which even enhances this effect. So this is all the variations with gas fractions, but there's also variations with galaxy stellar mass function, as well as a different AGN subgrid implementation, where they are kinetic jets instead of through the fiducial thermal model. And these variations are shown in this figure. And one of the main takeaways is that, for instance, when comparing the dark green curve to the lighter green curve, that you see that these are two simulations where the only thing that varies is the AGN subgrid model, but other than that, everything is kept the same. That you see that there are actually some different signatures. The behavior is different, although the suppression is roughly the same. You do see that for jets it still increases with kappa, whereas for the fiducial L1M9 it decreases after 0.1. So the details of the subgrid model do impact the feedback, which is which need to be understood more to eventually use this to the fullest extent as possible. Now we can also compare these distributions in the cosmology variations. So that's what's shown in this figure. So in this case, I compare the dark matter only simulations of the L1M9, the fiducial model, which is a DES year 3 plus all external cosmology, to a Planck model, and two Planck models with heavier neutrinos, the Planck new OP24, and finally a low S8, LS8 model. So the bottom panel again shows the ratio to the fiducial DMO model. And now you can see that the first thing to note is that the variations are larger than the baryonic variations, which is a good thing if you're interested in constraining cosmology. However, the second thing to note is that also these signatures may be a bit degenerate with baryonic physics. So for instance, especially the heavy neutrino model does show the same suppression signal and behavior as some of the baryonic variations. So this will complicate an inference, and you really need to understand the baryons good enough to also be able to unbiasedly constrain cosmology. But there is some prospect for modeling these peaks, as we also explored the baryonic suppression at different cosmologies. So there's these 5 different cosmologies. And now for each of the cosmologies, we compare the hydro signal to the DMO. And we see that the baryonic suppression, as indicated by the bottom panel here, is independent of the cosmology for the cosmologies we considered. So this does indicate that at least you can analyze the variations for cosmology from DMO only, and that you can do it separately from the hydrodynamical impact. Now, this is only looking at number densities of weak lensing peaks in the weak lensing convergence strength. But the next thing we do is we also assign a redshift to each of these peaks. So for this, we again use the FLAMINGO light codes, and now we can really see in the simulations, okay, where is the halo, where is the overdensity that causes this peak, and then we attribute each peak to each halo individually, and that's what's shown in this figure. So this figure shows background is an overdensity, projected overdensity shell, and then in the yellow circles indicate the weak lensing peaks that have been assigned to the shell, and in the red dotted circles indicate the halos to which these peaks are matched. And this clearly shows that, well, these peaks are matched to their proper halos, which are these massive overdense structures in the simulations. Um, yeah, and then there's several things to do. We can do with this. So first, I show the purity and the completeness. So focusing on the left figure first, this shows the purity, so the fraction of peaks, basically as a function of all peaks. For in the solid curves, the single shell peaks, so peaks which are clearly from a single shell in the Flamingo simulations. Then dash dotted noise peaks. So these are peaks where at least half of the final peak values can be explained from considering the shape noise that has been added at the end alone. So these are peaks that, well, can be attributed to noise. And then finally, multiple shell peaks as indicated by the dashed curves. So these are peaks where we see that there are actually multiple shells that contribute to the signal. So these peaks are caused by a superposition of different objects along the line of sight. And then the top panel is for Euclid, whereas the bottom panel indicates the kid slide prediction. And you see clearly the improvement of the next generation of weak lensing surveys that is able to get a much purer sample for lower kappa weak lensing strength. And especially if you look at the numbers, so kids will have roughly only on the order of hundreds signal to noise larger than 5 peaks, whereas for Euclid it will be 10 to the 5. So then you can really do cosmology. So what I then do is I select all the peaks with a signal to noise larger than 5, and then I select the halos to which they have been matched. And then on the right hand side, for all of the halos in the simulation, I check which of them have been matched to a peak and then binned in halo mass. So what's shown here is that especially for up to a redshift of roughly 0.05, you see that the completeness of the most massive halos is very good. For the most massive bin, it's even perfect, up to redshift of 0.5. And then also the lower mass bin also has a good completeness. And this is definitely comparable or even better than, for instance, current state-of-the-art cluster abundance inferences. So I've matched all these peaks to halos, and then we can also assign redshift. But first, we also show the number density of weak lensing peaks now binned in halo mass. So that's shown what's here. So darker colors in this plot correspond to more massive bins, so more massive halos. You see that on average, more massive halos cause higher weak lensing peaks, as you would expect. But also that if with the selection of peaks that I made, you see that a lot of or all of them can be, many of them can be attributed to 10 to the 14 and over halos and more massive halos. So these will be these will be the halos that have to be carefully modeled if you wanna analyze these peaks. And this can also highlight what other observables to use, for instance, when comparing these peaks. For example, radio or SZ. Um, yeah, and then we assign a redshift to each of these, or use the halo redshift of each of these peaks, and then we bin in redshift. So there's now a redshift distribution for, again, L1, M9, which is the fiducial model, and then also models with a higher and a lower mass resolution and more measurements from a larger box. So this indicates the numerical convergence, which is great for our measurements. But this is mostly to show the shape of the distribution, because for the next figure I'm showing all the baryonic and cosmology variations, but now compared to the green curve in this figure. So that's been divided out in the next figure. And I should say that we also we distort the true redshifts accordingly to the accuracy we expect Euclid to have for these kinds of objects. Yeah, so this is now the redshift distributions divided by the fiducial redshift distribution, as I showed in the previous figure. And now the left and the central panel show the baryonic variations that Flamingo has, and the right panel shows the cosmology variations. So if we first focus on the baryonic variations, the important thing to note is that all the curves are flat, they're horizontal. So this shows that the redshift evolution is not different from the fiducial model. There's an amplitude difference as I apply a fixed signal to noise cut, and we saw that uh, simulations with stronger feedback there are at a fixed kappa there are less peaks there with the large convergence values, but this plot shows that the redshift distribution of those peaks it has the same shape as the fiducial model. And this even holds for the very strong feedback model and also the DMO signal even. If we now focus on the right-hand panel, this shows the cosmology variations. There are different signatures. So especially all the heavier neutrino models, as well as the LS8, the low sigma 8 model, they show an increasing difference at higher redshift. So this shows us that we can actually use this to make sure well to disentangle some of the degenerateness that we saw before, and now disentangle the cosmology physics from the baryonic physics by including the redshift information of these peaks. However, it's not perfect, as you can see. For instance, the Planck model it also has a flat curve, and we can understand all these cosmology variations to actually the impact of the different parameter values that they have, for instance, omega m on the halo mass function, therefore the number of peaks that we actually see, which probes this halo mass function at different redshifts. So for instance, Planck has a higher omega m and therefore more peaks, which is again this amplitude difference that you see. And then the final two models, Planck CDM 12 and 24, are Planck models with decaying dark matter. You see that they have a great suppression, but the signature is also flat. But this just shows that there's a great prospect in using these peaks. And of course, if you would then combine them with other statistics, non-Gaussian statistics, which in their own way are also sensitive to baryonic physics and cosmology, you can combine them all to jointly constrain baryonic feedback or calibrate baryonic feedback while constraining your cosmology. Okay, to summarize, I've told you about the baryonic impact and the impact of cosmology on weaker gravitational lensing convergence peaks in the FLAMINGO simulations. I've shown that the baryonic suppression can be understood well from considering the impact of feedback on single halos, and the cosmology differences can be understood from the impact of cosmological parameters on the halo mass function. I've shown that the variations induced by cosmology are bigger than baryonic variations. However, there are degenerate signatures between the two different effects in the number density of weak lensing peaks. However, the redshift distributions do not depend on baryonic physics, and therefore this highlights that there's great possibilities in jointly constraining cosmology while also calibrating your baryonic model.